Okay, in this video we're going to talk about the Laplace transform. And the Laplace transform is something that you can use to solve differential equations. A lot of differential equations. And so this is what we're going to be talking about in the next several videos. So what is the Laplace transform? So here's the definition. Suppose that you have a function f. Oh, hold on. I need to make sure. Oh, what did I do? Oh, jeez. One second. Okay. Yes. Okay. Suppose that you have a function f, which is defined on the interval from 0 to infinity. We're going to define a new function, which is called the Laplace transform of little f. The Laplace transform of f is defined to be the function f, function capital F, defined by capital F of s. So, well, I'm just going to write down. It's the integral from 0 to infinity of e to the minus st little f of t dt. So this is a weird definition. Let's just talk about it for a little bit. So you have some function little f of t, and then the Laplace transform, which is sometimes written as L of f, like this. That function, what it does when you plug in an s is you take the integral from 0 to infinity of e to the minus st times little f of t. So for instance, for example, if you plug in 1 into your capital F, that is going to be the integral from 0 to infinity of e to the minus t little f of t. Right? So e to the minus t f of t, when you integrate it from 0 to infinity, you're going to get some number. And that number, what you get is capital F of 1. So this is a function. This is a function of s. So notice that the little f, you can think of it as something that you plug in to capital L. So capital L is taking the function little f as the input. So that's the input. And it's spitting out a new function, capital F. And it's typical to use the notation that little f is a function of t and capital F is a function of s. Okay. And notice that this is an improper integral from 0 to infinity. So let's just recall what that means. It means that you take the limit as n goes to infinity of the integral from 0 to n. So you may want to review improper integrals if this is unfamiliar to you. Let's look at this example. What's the Laplace transform of the function f of t equals 1? And this is, remember, when your function is only defined from 0 to infinity. What is the Laplace transform of this function? Well, we will use the definition. The Laplace transform, capital F of s, is defined to be the integral from 0 to infinity of e to the minus st little f of t. And that's going to be the same as, in this case, little f of t is 1, so it's going to be the integral from 0 to infinity of e to the minus st dt. Now you're integrating with respect to t. So when you integrate, when you do the definite integral, this is definite integral, right? There's bounds of integration. When you do that, the t is going to go away, and you're going to get something with only s in it. So in this case, you are going to get, well, we have to, let's just do it kind of the correct, proper way, which is you express this improper integral as the limit of just ordinary integrals, 0 to n of e to the minus st dt. So now we have to evaluate what this definite integral is. That's going to involve an n, and then you take the limit as n goes to infinity. So this is going to be the limit as n goes to infinity of what is integral. We're integrating with respect to t, and we're treating s as a constant. So you're going to get negative 1 over s e to the minus st. Do we agree with that? Because when you take the derivative, because of the chain rule, you're going to multiply by minus s, and then that's going to cancel with a negative 1 over s. So you're going to get that evaluated from 0 to n. Now what is that? Well, it's going to be negative. So what are we plugging in n and 0 into? S or t? We're plugging them into t because we're integrating with respect to t. So you're going to get negative 1 over s e to the minus sn minus negative 1 over s e to the minus s times 0. And what is that going to give you? That's going to give you the limit as n goes to infinity of negative 1 over s e to the minus s capital N, and then this minus minus is going to be a plus 1 over s, and then you have an e to the, well, this exponent is going to be 0, e to the 0 power is 1. So you're just going to have 1 over s, and now we're going to take the limit as n goes to infinity. Now if s is, so you have this e to the minus sn, right? This. If s is positive, then what happens is n goes off to infinity. You're going to get e to the negative n, or you're going to get e to something where the exponent is going to negative infinity. So when you do e to that, what's that going to approach? That's going to approach 0. Do you see why? Because it's like 1 over, that's 1 over e to the sn. And if s is positive, so you have like, you know, something like this, then as n goes up to infinity, you get 1 over something, and then the bottom's going to go to infinity, so this is going to approach 0. So you're going to get, when you evaluate the limit, you're going to get 0 for the whole thing. So you're going to get negative 1 over s times 0 plus 1 over s, and then negative 1 over s times 0 is 0, so you're going to get 1 over s. So your Laplace transform of 1 is going to be 1 over s for s greater than 0. And when s is less than or equal to 0, does this limit, what's going to happen with this limit? Well, first of all, when s is 0, you can't even do, maybe instead of less than or equal to 0, let's just talk about what happens when s is less than 0. So when s is less than 0, you're going to get this limit's not going to exist. So f of s does not exist. Capital F of s does not exist. When s is 0, well, you have to do this separately. So you have to do f of 0, capital F of 0 is the integral from 0 to infinity of e to the minus 0t f of t dt, and that's going to be, well, e to the negative 0t is e to the 0, that's 1. So you're going to get the integral from 0 to infinity of f of t. Well, f of t is 1, right? Now, what's the integral from 0 to infinity of 1? It doesn't exist. I mean, it would be infinite. So f of 0 does not exist. And so what's going on is your function is f of s is 1 over s, where the domain is s is greater than 0. That's the Laplace transform of little f of t equals 1. Okay, so that was the Laplace transform of the constant function 1. Let's do another example. What's the Laplace transform? So a is a constant. What's the Laplace transform of e to the at? Well, again, we're going to use the definition. It's capital F of s equals capital F of s is the integral from 0 to infinity e to the minus st f of t dt. And our f of t is e to the at, so this is going to be the integral from 0 to infinity, e to the minus st times e to the at dt. And we have to evaluate this integral. Now, we have a product, e to the minus st times e to the at, and there's generally no easy way to integrate a product of two functions, but what can you do with these two functions to make it something you can integrate? You can use those properties of exponents, that when you have e to the x times e to the y, excuse me, that's the same as e to the x plus y power. So let's use that. So we can rewrite the integral as the integral from 0 to infinity of e to the minus st plus at. And now what can we do to the numerator? I mean, not the numerator, the exponent. We can factor out the t. So this is going to give us e to the minus s plus a t dt. And remember, we're integrating with respect to t, so our negative s plus a is a constant. And we can do this integral. This is just going to be 1 over negative s plus a e to the negative s plus a t evaluated from 0 to infinity. Okay. So this is going to be the limit as n goes to infinity. I can even move the negative 1 over negative s plus a out, like this. And it's going to be the limit as n goes to infinity of e to the minus s plus a t from 0 to n. Because I don't want to be plugging in infinity. Okay. So, oh, and I can rewrite the top as negative 1 over s minus a. Does that might be a little easier. Okay, so the limit as n goes to infinity of e to the minus s plus a n minus e to the n, and when you plug in t equals 0, you're going to get e to 0, which is 1. So 1. And you're taking the limit as n goes to infinity. Well, again, we have this issue where if, is that right? Is it s plus a? Negative s plus a. Oh no, I didn't factor this. I should have factored out the minus here. So it should be s minus a. Like that. Like that. There we go. Okay. we have this issue where as n goes to infinity, okay, when we're analyzing this e to the thing is going to go to 0 if the exponent is going to negative infinity. And that's going to happen if s minus a is positive. Because if s minus a is positive, then as n goes to infinity, the numerator is going to approach negative infinity. Not the numerator, the exponent is going to approach negative infinity. So if s is bigger than a, then this limit here is going to go to 0, and then you're going to get 0 minus 1. So you're going to get, this is equal to negative 1 over s minus a times negative 1, and negative 1 times negative 1 is 1, so you're going to get 1 over s minus a for s bigger than a. So that's f of s. And if, what happens if s is less than a? Well, if s is less than a, right? So if s is less than a, then s minus a is negative, and then you're going to get negative number times n, so you're going to get a positive, you're going to get like a positive constant times n. And as n goes to infinity, e to that's going to go off to infinity, so the limit's not going to exist. So this is only defined when s is bigger than a. And what happens if s is equal to a? Well, if s is equal to a, so let's just write, if s is less than a, f of s does not exist. Okay. If s is equal to a, well, if s is equal to a, then we don't have, you can't do this integral like this. Because you're going to get 1 over negative s plus a is going to be 1 over 0. That's undefined. So instead you have to do it separately. If a is equal to s, then what you get when you do the integral, before you're doing the integral, it's the integral from 0 to infinity of negative e to the minus st times e to the at dt. And then if s is equal to a, that's the integral from 0 to infinity of e to the minus at times e to the at dt, and then those are going to give you 1, and again you have this, and then this doesn't exist. So f of a doesn't exist either. And so the Laplace transform really is capital F of s equals 1 over s minus a, where s is bigger than a. So the Laplace transform is not defined if s is less than or equal to a. Okay. A couple more examples of this, computing the Laplace transform. Let's calculate the Laplace transform of sine of bt, where b is a constant. So again, we're going to use the definition. So this is equal to the integral from 0 to infinity of e to the minus st sine of bt dt. And this is going to be the limit as capital N goes to infinity of the integral from 0 to n, e to the minus st sine of bt dt. Now I'm not going to go over how to do this integral. This is one of those integrals that's annoying. You can do tabular integration if you know what that is, or I think this is one where you can do integration by parts twice. And instead of spending all the time doing this, because this is really like a Calc 2 thing, this is one of those things where I think it's okay to look it up instead of having to do it all out. So I'm just going to skip how to actually do this and then jump straight to what you get. And what you end up getting is, when you do the integral, it's e to the minus st over s squared plus b squared times negative s sine bt minus b cosine bt from 0 to n. Okay, so we have to evaluate what that is, and then take the limit as n goes to infinity. And that is going to be the limit as n goes to infinity of k. So we're plugging in n everywhere we see a t. So e to the minus s capital N over s squared plus b squared times negative s sine b capital N minus b cosine b capital N. And then we have to subtract what you get when you plug in 0 for t. Well, when you plug in 0 for t, let's look at what you're going to get. You're going to get e to the minus st. When t is 0, that's e to the 0, that's 1. So you get 1 over s squared plus b squared. And then when you plug in 0 into your sine bt, you're going to get sine of 0, and that's 0. And then you're going to get negative b times cosine of bt. So that's cosine of 0, cosine of 0 is 1. So you're going to get a negative b like that. So let's just write out what you have neatly. So it's e to the negative sn over s squared plus b squared times negative s and we can even factor out a negative just to make it a little. So let's put a negative here and then pull that out of the parentheses. So you're going to get s sine bn plus b cosine bn. Okay, and since this s squared plus b squared doesn't involve, this s squared plus b squared here doesn't involve n, you can move that out. It's the property of the limits. So 1 over s squared plus b squared, limit as n goes to infinity of s sine bn plus b cosine b capital N. I'm going to write this as over e to the s, oh, and there's a negative, and then over e to the negative, e to the sn. So I'm just rewriting it with a reciprocal. Now let's see what the limit of this is. So if s is greater than 0, what's going to happen? Well, the denominator is going off to infinity. What about the numerator? And here's where you use your facts about sine and cosine, that sine and cosine are always between negative 1 and 1. So the absolute value, say, of s sine bn plus b cosine bn is less than or equal to the absolute value of s sine bn plus the absolute value of b cosine bn. That's just the fact about absolute values, that when you have the absolute value of a plus b, it's less than or equal to the absolute value of a plus the absolute value of b. Now this we can split up as the absolute value of s times the absolute value of sine bn plus the absolute value of b times the absolute value of cosine bn, using another property of absolute value, that the absolute value of xy is equal to absolute value of x times absolute value of y. Now this, what can you say about the absolute value of sine of anything? Sine is always between negative 1 and 1. So this in absolute value is going to be less than or equal to 1. And similarly, the absolute value of cosine of bn is less than or equal to 1. And so therefore, you have something which is less than or equal to the absolute value of s plus the absolute value of b. Okay, that's true no matter what s is. So if s is, so you have something where the numerator is less than or equal to some constant that doesn't depend on what n is. And so, so then the denominator is going off to infinity, and because of that, the limit's going to be 0. I mean, one way to to write this in more detail, if that's not clear, is to say that this thing that we're finding the limit of in absolute value, we're trying to explain why if s is greater than 0, this limit's going to be 0. If you take the absolute value of this, this is less than or equal to absolute value of s plus absolute value of b over e to the Sn. Okay, I mean, I guess I'll put absolute value. It doesn't really matter because e to the Sn is always going to be positive anyway. And then this thing in the middle is less than or equal to negative absolute value of s plus absolute value of b over e to the absolute value of e to the Sn. Okay, now as n goes off to infinity, so you, on the left and right, you have a constant over something that's going off to infinity. So this is going to approach 0 as n goes to infinity. And this is also going to approach 0 as n goes to infinity. So by the squeeze theorem, the inside, if you have something that's stuck between two things on the top and bottom, and the top and bottom are both approaching 0, as n goes to infinity, then by the squeeze theorem, or by the sandwich theorem, whatever you want to call it, this inside thing is also going to 0. As n goes to infinity. And if the absolute value of something is going off to 0, then the thing inside is also going to 0. So s sine bn plus b cosine bn over e to the Sn is going to 0 as n goes to infinity. If s is positive, right? So that if s is positive comes into play here when you're showing that the denominator e to the Sn is going to 0 as n goes to infinity. Now if s were negative, then that would not be happening. Okay? So when I say going to 0, I mean this whole thing is going to 0, right? That's going to 0, that's going to 0. Okay. And so what are you going to get, going back to this whole thing, here, oh, and I have a plus b over s squared plus b squared here. I kind of forgot that. So plus b over s squared plus b squared, right, from here. So what's going to happen is if s is greater than 0, the Laplace transform, this whole limit's going to be 0, and so you're going to get b over s squared plus b squared. B over s squared plus b squared. What happens if s is less than or equal to 0? Well, if s is less than or equal to 0, okay. So first of all, if s is 0, you're going to get the integral from 0 to infinity of sine bt dt. Now that integral, does that integral exist? That integral doesn't exist. Because let me think. Because that's going to be the limit. Maybe b is a non-zero constant here. If s is 0, then you're going to get the limit as n goes to infinity of negative 1 over b cosine bt, or cosine b bn, like plus 1 or something, plus negative 1 over b plus negative 1 over b. And the limit, that limit doesn't exist because cosine is oscillating, so it doesn't exist. So if s is 0, this Laplace transform doesn't exist. If s is negative, then you get e to some positive thing times t sine of bt. And then what happens is this integrand, e to the negative st sine bt, if s is negative, that's going to go off to infinity. And negative infinity, it's going to oscillate, because you have sine oscillating between negative 1 and 1. So if s is negative, then this function, e to the minus st sine of bt, is gonna look like, okay, it's gonna, as t goes off to infinity, it's going to just like be like that. And it's gonna keep going off like that. It's gonna get bigger and bigger and bigger, and then more and more negative, and go up more positive, then more negative. So the integral is not gonna exist. Okay. Yeah. Because for the improper integral to exist, the area has to be approaching a certain number, right? That limit is going to be the integral. So the graph is going to look like that, and so the integral doesn't exist. And so this shows that the Laplace transform is this, where s is greater than 0. Okay. Let's do another example. What's the Laplace transform of little f of t, which is 2 if t is between 0 and 5, 0 if t is between 5 and 10, and e to the 4t if t is bigger than 10. So again, we have to use the definition of the Laplace transform. So let's set it up. It's the integral from 0 to infinity of e to the minus st f of t dt. Now your f of t is going to depend on what t is. So it's a good idea to break this up into 3 different pieces based on these intervals. So I can write this as, I can split up the integral from 0 to infinity as the integral from 0 to 5, plus the integral from 5 to 10 plus the integral from 10 to infinity. And then just do each of the integrals separately. Because when t is between 0 and 5, your f is 2. So you're going to get the integral from 0 to 5 of 2e to the minus st dt. And then you're going to get the integral from 5 to 10 of 0. That's going to be 0. Then plus the integral from 10 to infinity of e to the minus st times e to the 4t dt. So this integral this is e to the minus st. That's going to give you negative 2 over s e to the minus st from 0 to 5. And that's going to give you negative 2 over 5 e to the negative 5s, and then minus negative 2 over s. Yeah, negative 2 over s e to the negative 5s minus negative 2 over s. Because you're going to get e to the 0, which is 1. So plus 2 over s. And then that's going to give 0. And then this is going to be the integral from 10 to infinity of e to the negative s plus 4 times t dt. And then that's going to be negative 1 over s minus 4 times the integral, times e to the negative s plus 4 t evaluated from 10 to infinity. And I'm going to skip the thing about the limit because at this point I think we can see what we're going to do. What happens to the top as capital N goes to infinity? Well, if s is greater than 4, then negative s plus 4 is negative. That's the same. So then you're going to get 0. And so you're going to get 0 minus negative 1 over s minus 4 e to the negative s plus 4 times 10. And so this is going to be negative 2 over s e to the negative 5s plus 2 over s. And then minus minus, you're going to get plus 1 over s minus 4 e to the 10 times, I'm going to write negative 10 s minus 4, where s is bigger than 4. So that's the Laplace transform. Again, if s is less than or equal to 4, this right-hand integral is not defined. So that's the Laplace transform. Okay, a few more things. So that was some examples of doing calculations with the Laplace transform. These examples that we just did. But we want some properties of the Laplace transform, it's just like when you're defining the derivative. First, you should do some examples using the definition of the derivative as a limit. But it's more convenient after a while once you have the basics, to use properties of derivatives, like the product rule and the chain rule and things like that. And there are going to be properties of the Laplace transform that we can use. So one of them is this theorem, which is the linearity of the Laplace transform. The Laplace transform operator. The operator that takes the function to the Laplace transform, that is a linear operator. Meaning that if you have the Laplace transform of like CF plus DG, this is going to be C times the Laplace transform of F plus D times the Laplace transform of G. So you can distribute the Laplace transforms. And in general, if you have the Laplace transform of, it doesn't have to be just 2, it could be just any finite number. So if you have C1 F1 plus C2 F2 plus dot 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 plus Cn Fn, and you want the Laplace transform of that, that is going to be C1 times the Laplace transform of F1. Hold on. Oh, I need to share my... Okay, plus C2 times the Laplace transform of F2 plus dot 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 plus Cn times the Laplace transform of Fn. Let's do an example, and let's do an example first before going into why this linearity property is true. So, example, what's the Laplace transform of 10 minus 5e to the 3t plus 7 sine 2t? Well, here we have, so 10 is 10 times 1, right? So we have this combination of functions. And we know the individual Laplace transforms. So we know that the Laplace transform of 1 is 1 over s, where s is greater than 0. And we know that the Laplace transform of e to the 3t is 1 over s minus 3, where s is bigger than 3. Right? And we know that from the previous, where is it? From this fact up here, that the Laplace transform of e to the at is 1 over s minus a, where s is bigger than a. And we found the Laplace transform of sine of bt, and we have a sine of 2t here. So the Laplace transform of sine of 2t is, remember, is b over s squared plus b squared. So it's 2 over s squared plus 4, as long as s is bigger than 0. So therefore, as long as, so you have three things. The first thing is true if s is greater than 0. The second thing is true is when s is bigger than 3. The second thing is true when s is bigger than 0. Now you want all three things to be true. So what does s have to be in order for all these three things to be true? So when you put them together, s needs to be bigger than 3. So yeah. And so now we can use the linearity property, because the Laplace transform of 10 times 1 minus 5 times e to the 3t plus 7 sine of 2t, by the linearity, this is going to equal 10 times the Laplace transform of 1 minus 5 times the Laplace transform of e to the 3t plus 7 times the Laplace transform of sine of 2t. And this is going to be equal to 10 times 1 over s minus 5 times 1 over s minus 3 plus 7 times 2 over s squared plus 4 as long as s is greater than 3. And now let's simplify this. This is going to be 10 over s minus 5 over s minus 3 plus 7 times 2 is 14. 14 over s squared plus 4. So it's going to be that as long as s is bigger than 3. So you have to say what the Laplace transform is as well as the domain. Because it's only when s is bigger than 3 that this is the Laplace transform. And it's undefined if s is less than or equal to 3. Because one of the Laplace transforms doesn't exist, right? If s is less than or equal to 3, then the middle thing doesn't hold. The middle, this one, is only when s is bigger than 3. Okay. Now let's see why the Laplace transform has that linearity property. Well, it's actually not that surprising if you think about it, because the Laplace transform of f is an integral, right? It's an improper integral. And integrals have a linearity property. Now the Laplace transform is not the integral of f. It's a Laplace transform of a different function. But you're still doing an integral. So if I have the Laplace transform, so y, the linearity of the Laplace transform, well, if I have the Laplace transform of cf plus dg, that's going to be, when I plug in s into that function, I'm going to get the integral from 0 to infinity of e to the minus st cf plus dg, right? This function of t dt. And by definition of this function, this is going to be the integral from 0 to infinity of e to the minus st times c times f of t plus d times g of t dt. And then I'm going to get, let's distribute the e to the minus st across. So I'm going to get the integral from 0 to infinity of c times e to the minus st f of, in fact, I don't even have to write it in that order. I'll just write it as e to the minus st times c times f of t plus e to the minus st times d times g of t. So I'm integrating this dt. Well, I can split up the integral, so I have an integral of a sum, right? I have an integral of this plus this. And when you have an integral of a sum, it's the sum of the integrals. I can write this as the integral from 0 to infinity of e to the minus st times c times f of t plus the integral from 0 to infinity of e to the minus st times d times g of t. And then I have the property of the integral that I have a constant. I have these constants c and d. And I can move the constants out. That's a property of the integral. So it's going to be c times the integral from 0 to infinity e to the minus st f of t dt plus d times the integral from 0 to infinity of e to the minus st g of t. Well, what is this? This thing is the Laplace transform of f, and that thing is the Laplace transform of g. So this is going to be equal to c times the Laplace transform of f evaluated at s plus d times the Laplace transform of g evaluated at s. So that's why the Laplace transform of cf plus dg is the same. Okay, maybe I'll just write out one more thing. This is what you get when you take the function c times the Laplace transform of f plus d times the Laplace transform of g and then plug in s. So you have these two functions, they do the same thing when you plug in s, and since they do the same thing, no matter what you plug in, they have to be the same function. So the Laplace transform of cf plus dg equals c times Laplace transform of f plus d times the Laplace transform of g. Okay, so we'll talk in a future video about when the Laplace transform exists, and then we'll talk about some properties of the Laplace transform, some more properties of the Laplace transform that we'll use. And then we'll talk about inverse Laplace transforms, and then we'll finally be able to use all of that and put it together to solve initial value problems.